begin with a word of prayer. Dear Heavenly Father, we thank you for this rain. I know it helps the forest fires around here. And just pray to help us to get dry soon. And help us to focus on just Laplace transforms today. Just try to understand what the Dirac Delta function is. And I just pray again, Lord, that you be glorified in what we do, Lord. In your name I pray. Amen. Okay, so we'll talk about the Dirac Delta function. I'll put some quotes on function. It's not actually a function. So basically the idea of this thing is, well, I don't know how to best introduce it, but imagine you hit a hammer. Right? Hit a hammer on a spring, you know? So this is a spring without friction. What we have? We have mass times acceleration, right? Is equal to minus kx plus the force of the hammer, right? So, what's that actually? That's Newton's equation, of course. But what does that actually look like? What's the net impact of, if you have? Let me just draw a silly picture here for a second. You got the spring, right? It's attached to some mass, right? And you imagine whoever with the, I can't draw worth anything here. He's got a sledgehammer, and but this doesn't quite do it justice because I want him to hit it. It's more, I think, more like golf, I guess. I don't know. All right. So he takes this thing and he just whacks it. He just whacks his spring like that, right? Hits the mass. Right? And that, it's going to set the mass into motion, right? How would you model a hammer hit to something? What would the force time graph of the hammer look like?
The hammer hits it at one point.
It just, basically, you know how a hammer, you hit it and then it just kind of draws off it, right? So the hammer hit, let's say the hammer hits at time t naught, right? What's the force of the hammer? What's the graph look like? Up till time t naught, it's not doing anything, right? So the force of the hammer is concentrated at that one point in time, right? And so the graph of that would look something like, of course, actual physical processes take some finite amount of time, right? So there's some sort of window of time, it's 0, and then right close to time t naught, there's a spike, right? And then it goes back to 0 again, right? So, but there's just this one, there's just one just concentrated spike of force with the hammer, right? And how could you describe that force? What would physically, what could you measure to relate to this spike? And there's really only one thing, because this delta t here, right, is so small that you really don't have hope of observing the details of the hammer hit, right? All you can kind of see is before and after, what's changed in the system. So you guys remember from classical mechanics, from your physics course, what's the interpretation of the area in the force time graph? Remember this? dp dt equals to f. So ignore the kx for a second here. Just imagine. I don't really need to put a spring there. I don't know why I did it to make it more complicated. That's dumb. I should just take the spring off it and just put a mass in there, just to focus on the hammer. It's just I want to solve spring mass problems where we hit them with hammers. So I'm just thinking ahead to what we want to solve. But so if you integrate this, right, what happens? Say from t1 to t2, what do you get? we get the change in momentum, right, is equal to the integral under the forced time graph. So that's the significance of area under a forced time graph. It gives you the change in momentum, or what we call the impulse, right? You guys work problems like this in physics, right? We threw a baseball against a wall, or a tennis ball against a wall, bounced off. You're asked what's the change in momentum, what's the impulse of the ball before and after, what's the impulse delivered to the tennis ball by the wall. And that's also kind of like this, right? There's this momentary impact, there's an impulse delivered, and that's kind of it. So what's the mathematics of this, right? How do you describe that mathematically? Well, that's what the Dirac Delta function does. So here's a definition. Delta, and this is sort of an informal definition. You'll have to forgive me for this. It's 0 if t is not equal to t naught, and it's infinity if t is equal to t naught. All right, a little bit weird. But that's just taking this to the extreme. Imagine delta t goes to 0, right? Basically, what's this graph? The idealization of this graph looks like what? Just a line, t equals t naught, right? So this is the idealization. And that's what the Dirac Delta function does for you. It gives you an idealization of this time increment squashing to 0. But the significance then, and this is a convention, is that this particular one has the following property. It turns integration into evaluation. So the integral from minus infinity to infinity of f of t times delta of t minus t naught dt, all right, is equal to f of t naught. That essentially sets the impulse of the Dirac Delta function to 1. That's why the Dirac Delta function is also known as the unit impulse function. It seems kind of scary. It's definitely out there. This is like nothing you've ever done before, right? Unless you had this in class. Do you guys have it in class already? Luke said it. You have more to say about this function there, obviously, but that's good. This is just what we need here. And so obviously the next question is, what's the Laplace transform of it, right? So, because if we can figure out the Laplace transform, well, you know, then we can solve differential equations that involve like spikes of force, right? Or spikes of voltage, or spikes of current, or whatever. So the Laplace transform of the delta function t minus t naught at s, and we're going to suppose that t naught is greater than 0. We don't know otherwise. And so that's the integral from 0 to infinity of, I mean, this guy is just kind of lazy, what I have right above here. To be more sort of magnanimous, we should say, where the Dirac Delta function, you know, just provides, it turns integration into evaluation. And this is going to be true for any function which is defined at least on some neighborhood of t naught. So you don't even have to have that f of t is defined for minus infinity to infinity. Of course, if f of t is only defined from like, you know, 0 to infinity, you can just extend the function to be 0 on the rest of it anyway. So it's not like a major imposition. You can always just throw zeros into the rest of the domain if you want. But anyway, that's not especially interesting, so let me stop thinking about it. We have e to minus st, right? Delta of t minus t naught dt, all right? And so you do that integral. Now this, I mean, I can't emphasize to you enough. Dirac Delta function turns integration into evaluation. So all you have to do is take the function here, which happens to be e to the minus st, right? And write what? E to the minus s t naught. There you go. Bam. Isn't that simple? It's very simple. So let's solve a hammer spring problem. let's see, consider mass 1, spring constant 1 with, let's say, y of 0 equals to, I'll keep it really simple, y prime of 0 equals to 0. And a hammer hits the spring at time t naught equals to 3 seconds and delivers an impulse of 10 what? What are the units of momentum? Yeah, kilogram times meters per second, also known as Newton seconds. Is that right? Or Newton second? Yeah. Okay, so, but again, let me put that in parentheses because you know by now I'm not going to write kilogram meters per second in my formula because it offends me and uglifies the problem, so I refuse. But, okay, so, here we go. What's our Newton's equation? We got ourselves a, oh, I guess I can bring myself to put, I tell you what, I'll make these both 1. It's more exciting if we do it that way. Fine, I'm going to regret that, but we need the practice, so let me do it. Fine. So our differential equation is y prime prime plus y equals to 10, and then delta t minus 3. Right? Does that make sense to you guys? Basically, the spring mass system is just sitting there, oscillating back and forth, minding its own business, and then we come and whack it with a hammer at time 3 and deliver 10, 10 units of momentum to it. This is the mathematical model for that. Now we can find the equation of motion using Laplace transforms. So, usual song and dance. Take the Laplace transform of this. That gives us s squared big Y minus s minus 1. All right, that's by, oh man, I forgot my formula sheet. You guys are a bad influence. Let's see here. It's like table 7.2. It's one of the ones in the, I can't read. Table 7.2, it's like the 1, 2, 3, 4, fifth one down that I just used. Yep.
Does it know which way the spring mass system is moving when this happens?
Nope. No. I'm assuming that I'm hitting the I think my picture would be more accurately for my problem, because it's if x is the positive, right? With a plus 10 there, it's going to go to the positive x. Yeah, you got a point. I don't know if that was your point, but it's true. If I wanted it to go that way, that would be, I'd put a minus there, right? Because that's our convention, that's our coordinate system. Okay, enough talk about physics 231. Let's see here, y equals to 10 delta of t minus 3. Oh, I'm sorry. I have to take the Laplace transform of the delta, right? What do I have? Really complicated. 10 e to the minus 3s. It's cool, right? Well, the coolness is short-lived. So let's see here, s squared plus 1 times y, right, is equal to s plus 1 plus 10 e to the minus 3s, right? And so this gives us y is equal to s plus 1 over s squared plus 1 plus 10 over s squared plus 1. Oh yes, my misgivings, my worry that I was going to surpass my calculational abilities for the day on this problem, vastly unneeded worries. See, because there's a vast difference between when somebody gives you a problem to solve where your force is discontinuous and it involves like a unit step function, you're fine, you just leave it there. You know, that's a pain, because when you get to this step, you end up dividing and you get something you have to do partial fractions on, like we did last time. But when we have the Dirac Delta function, that doesn't happen because there's no function of s next to the exponential. So like when we divide by s squared plus 1, we just get 10 over s squared plus 1, which is a harmless, lovable fuzzball of a thing to inverse transform, right? Like everything here is easily inverse transformable. I remind you that the inverse Laplace transform of 10 over s squared plus 1 is simply 10 sine of t, right? And the inverse Laplace transform of s plus 1 over s squared plus 1, I should have made this problem uglier. I almost made it too easy. This is equal to, well, that gives us a cosine t plus sine t, right? But the thing is, when we calculate the inverse Laplace transform of, let me call this thing f of t, and let me call this thing big F of s, all right, because I want to use a theorem. So we have f of s, right, times e to the minus 3s. How does that inverse Laplace transform go? Remember, what we do is we do f of t minus 3 times u of t minus 3. Of course, you guys have had a whole Thanksgiving break to study these things, so by now you're more in tune with this reality than even I am. Like you've done all your homework. You're just like, I want the test Thursday. Don't even give me an extra weekend to work on it. Let's go now. It's go time. Right? Okay. Yes, of course. You're like, finally, a Thanksgiving break. I'm not encumbered by all these annoying other things like, you know, friends and social activities here at Liberty or courses on things other than math. Finally, I have a break. I can just do math for 10 days. This is amazing. Sorry it had to end. But anyway, let's see here. So, do you guys know what I'm talking about? We derived this last class? Yes? So, the way that looks here, f is this thing. So that's 10 sine of t minus 3, u of t minus 3. And so in summary, we get y of t equals to cosine t plus the sine of t plus 10, 10 times the sine of t minus 3, u of t minus 3. Let's see here. You know, you can. Well, anyway, you can make this answer prettier, but I think I'm just going to leave it right there. So that's that. So do you understand the structure of the solution? What's going on here? Heuristically speaking, I'm not going to do a super careful graph, but it's originally at 1, right? It's got position 1, and it's got velocity 1, right? So these two things combine into like the square root of 2 times the sine of t plus some phase angle, right? So it's got an initial amplitude of like root 2. So it's going up. Here's your. So it goes up root 2, come back down. Let's see. I don't know where it is when t equals to 3. Where is it? Where does this thing get to? At t equals to 3. What's cosine of 3 plus sine of 3? Sine of 3 is just about 0. Cosine of 3 is like minus 1. So I guess it's gone all the way down here, something like that. Oh, just minus 1. So it's not all the way down there, something like that. And then what happens? Then you add this, right? So a little bit past. So you got like cosine t plus sine t for 0 less than t less than 3, right? And then after that, you got what? You got cosine t plus, fine, let me do a little bit of algebra here. That sine of t minus 3 is what? it's sine t cosine 3 minus the sine of 3 cosine t. So after time 3, we've got like cosine of t times 1, cosine of t times 1 minus sine 3. Forgive me if I'm plus the sine of t times what? Times, I got my 1 from the start, it's still there, and then this gives me plus cosine 3. Now, if I remember right, my trigonometry, the amplitude of the end, the final amplitude, is going to be the square root of 1 minus the sine of 3 squared plus 1 plus the cosine of 3 squared. Right? Basically because sine and cosine are perpendicular functions in some sense, so their magnitude, if you want to find the magnitude of a sine plus a cosine of the same phase angle, they have the same phase angle, right? So I'm pretty sure that the amplitude of this sine plus this cosine is just that, square rooted. And that's, well, that's like 1, right? Cosine of 3 is like minus 1, so basically this is gone. Like this is very close to 0. This is pretty close to 1, so the amplitude's more like 1. So after the hammer hits, it kind of just does some kind of like, basically it dampens the motion a little bit because you're hitting it. It's going in the, this is x, this is t. So as you hit it, at this point in the motion, you're hitting it this way. You're dampening some of its downward motion, and it ends up with just a smaller amplitude as it goes on. Yeah. I start to think that maybe I should start this course with like a 2-lecture thing on how to add and to manipulate sines of cosines and angles. I don't think you guys actually know this stuff. Do you really understand that the amplitude of the cosine plus the sine is this? No, I don't think you've seen that in a class before, have you? No. It's too late for us, but next semester. I think I had some homework problem earlier on which dealt with that, but then again, maybe I'm remembering a dream or another semester, so. What? Okay, so this brings us to our next topic. So you shouldn't be scared of Dirac Delta functions. What my larger point here, don't be scared of them. They're easy. They actually give you nicer problems to solve. Like if you're given a choice between solving a spring mass problem with a unit step function versus one with a delta function, choose the delta function. It has a smaller, like if this was a unit step function, we'd have cubics we'd have a cubic polynomial in S next to, in the reciprocal next to the exponential, then we had to do partial fractions on it like we did before. With the delta function, just basically after a unit impulse, you still have just some kind of, I mean, long story short, basically is saying if you hit it with a hammer, the motion of the spring after the hit, it's still the same kind of motion. Like it's sines and cosines beforehand, it's cosines and sines afterwards. If it was a spring, if it was a spring with damping, it'd be the same song and dance because you'd still have the same characteristic equation you're dividing by before and after. So the kind of thing you have here and the kind of thing you have here would both give you the same sort of inverse Laplace transform. They both be either sines and cosines or damped sines and cosines. Okay, so there's another tool that, fine. Why can't you trust me to just start it without me plugging it in? No. Thinks it's so smart. Yeah. It appears that, all right, there. Stop. Come on. I'm not worthy. All right, yes. Yes, Luke?
Why do we say that the delta function is almost function?
Oh, because it's impossible to have an integral of a function give you something non-zero based at just one point being non-zero. This is not how functions behave. And saying that the function is equal to infinity is also, a little dicey. Oh, God. I wish you'd asked that question like 30 seconds ago. So the other thing is, just one more comment here before I get into that. So if you look at the unit step function, right? So here's, y equals to u of t minus t naught, right? What's the derivative of this function? You're like, well, the derivative of this function is 0, right? Here's the derivative. Let me call this f. Well, this marker is not good for us. And then it's 0 over here, right? So it's 0, except what? Here, where we jump from 0 up to 1, right? So I'm sorry, it's 0. It should be down here, 0, not up here. That's 1, right? So what is this? Well, this is a spike, right? So I'll never forget. I'll never forget. I was taking one semester. I was taking real analysis, which is like one of the pickiest math classes you can take, right? And at the same time, I'm taking the junior level electromagnetism course. And in the electromagnetism course, I'm being mocked because the professor asks us, he's like, what's DDT? What's DDT of this? What is this? And then he make fun of us because we couldn't tell him that this was the Dirac Delta function of t minus t naught. I mean, obviously it's that, right? But the thing is, this is so much mathematical heresy because you're differentiating a function which is not continuous. What's one of the first things you're taught in Calc 1? That's right. Every differentiable function is continuous. So if you can differentiate it and it's not continuous, that's very what? Right? So on the one hand, we have that heresy. On the other hand, we have this thing, which is infinity at a point. But anyway, the point is this calculus is not the calculus of real valued functions of real variable. This is actually part of a larger thing called the theory of distributions, which was proved and established formally and rigorously by a mathematician named, I think Schwartz it was, some decades after this was introduced by physicists. It is Dirac's, Dirac, one of the forefathers of quantum mechanics, invented this thing and showed us how to write physics in terms of it. Another thing you can do, if I want to, say, suppose you got a charge right here, right? A point charge Q in XYZ space, right? And what's the charge density for this? Rho is usually we use for charge density. Well, rho is equal to Q times the Dirac delta function of X times the Dirac delta function of Y times the Dirac delta function of Z. Actually, that's not quite right. The Dirac delta function of R minus R naught is what we would write. That puts a charge at position vector R naught. Basically, if you integrate rho dV over some volume, it's case-wise defined. It's either Q if R naught is in the volume, or it's 0 if R naught's not in the volume. So this Dirac delta function is very, very important to physics. It gives us a mathematical device to encapsulate what it means to say you have a point charge. Now you could say that that's just a mathematical idealization, and that may be the case. Maybe it is the case that point charges actually do have some kind of finite extent. But so far as I know, we do not know, quote unquote, how big an electron is. So since we don't know that, this is a very good model for it. What's that?
Like the width of an electron?
Yeah, how big is an electron? Yeah, we don't know. Hey, come back. Okay, so next on our list of things to do is something called convolution. So let me show you about that. So I'm going to show you a derivation because I think it's really pretty, and you should see it. Because if I just give you the convolution as a formula, I could do that, right? But I think it's much better for us to understand where it's coming from, this formula. So, but on the other hand, I don't want to burn 20 minutes of class time working through it, so I just want to point to you. Now this PDF we're looking at right now is transfer functions. That PDF, that's on my main web page. I'll send you a link if I haven't already. It's already there, but it's not under your, I don't know if, it may be under your course page too. I don't know, my website is in disrepair at the moment. I need to fix some things, but okay, so here it is. Basically, this is the thing. We want a formula so that, I mean, like the Laplace transform of a function times another function, just plain multiplication. It's not the case that the Laplace transform of f times the Laplace transform of f times g is equal to the Laplace transform of f times the Laplace transform of g. That's just not how it works. All right. For example, if you look at like sine squared, right? Sine times sine. The Laplace transform of sine times the Laplace transform of sine would give you something like 1 over a quartic. Bs squared plus 1 is quantity squared. But sine squared t is 1/2 of 1 minus cosine 2t, right? Laplace transform of that is 1 over 2s minus s over s squared plus 4, right? So there you go. There's an example. The Laplace transform of product is not the product of the Laplace transforms, at least for the ordinary product. The idea of convolution is to find a modification of the ordinary product such that the convolution of f and g is, in fact, the Laplace transform of the convolution is the product of the convoluted functions. So this is the goal. The Laplace transform of f star g is going to be Laplace transform of f times Laplace transform of g. So if you set this goal in mind, what does that force you to make the formula for f star g to be? Just work it out. So plug it in, right? Here's the Laplace transform. And this is what we want. We want it to be this times that, all right? Giant jump right here. So I'm just going to combine it into an integral, a doubly infinite integral. And I mean, it's not too big a jump. It's just a jump. So although at the moment I thought, when I wrote this notes, I was like, jump! So anyway, I sometimes feel that way still, but sometimes less so. It depends on what other mathematical heresies I've committed in that day. Being that I just talked about the Dirac Delta function, this seems rather benign. So anyway, so e to the minus st times e to the minus su, of course, gives you e to the minus st plus u, right? So then you make a substitution, t plus u equals to w. And so d in t, of course, is also then going to be equal to, solving for t, w minus u. So I get rid of my t for w minus u. I get rid of my u for u. Oh, wait a minute. No, we like u, so we keep it there. And then, so there's my w. All right, great. Then what do I do? Put some parentheses here. Oh, so this integration is over u. That's a function of w, so I can pull it out. See that? Make sense? Pull this out, keep the integration over u inside. So all of the u dependence is right there. We do that integration. Then we integrate with respect to w. So let me scoot down here a bit. Now I'm going to make a change of variables just to make it more familiar. So here I changed my w to t just so you can see what it is. So we're looking at, this is the Laplace transform of whatever's in here, right? Like, this is e to the minus st times some function of t, right? dt. So this is the Laplace transform of this contraption. So this contraption is what we should call the convolution of f and g, because it will have the required property. Yep.
Can you just clarify quick how we turn the infinity in the upper integer of the right side function t?
Oh yeah, I don't think we ever explained this in Calc 3. I mean, do you remember when we spent a week on doubly infinite integrals? I mean, I didn't do that.
Maybe that you did.
I don't think. I mean, I may have done an example.
Wang did, because I was in his class last semester.
And whose?
Wang.
Oh, Wang? Oh, okay. I mean, I think this makes sense if you think about. So this, it's kind of guilt by association. If t is going to infinity, right? Out here, then this is also going to infinity. So, admittedly, there's another jump right there. Good call. But I think it's a reasonable one though, right? If these are both going to infinity, I can still make this inside integration have a bound which is getting larger and larger and larger if I connect it indirectly to this other bound, because this t is going to infinity. So, well, if t is going to infinity, t is going to infinity. The thing you might quibble over is these are independent infinities. So now you're saying that they're both going to infinity at the same rate. How do you have the right to do that? I don't think I do. I think there's some analysis missing there. Yeah. But anyway, on the other hand, from another perspective, you know what? This is not a proof. This is like a derivation. It's an argument. We're searching for a formula, right? So you're allowed to make some kind of jumps like that when you're looking for a formula. At the end of it, you make a definition, right? And then you prove things about the definition from there. So this is just to motivate really this definition. The convolution of f and g of t is equal to the integral from 0 to t, f of t minus u, g of u du. And there it is. So that's the convolution. Now, if I just wrote this down for you, if you're like me, you'd be like, why? Right? I mean, I don't look at that formula and go, oh, well, of course that's what the convolution should be. I don't know about you, but I mean, I don't. Now that we have it, we can prove properties of it, though, right? Like, it's pretty obvious that we have linearity, right? If I have f1 plus f2, well, first of all, if I put 0 in here, if one of my functions is 0, it's pretty obvious it convolutes to 0, right? Because if I have a 0 function here, then we integrate 0, which gives me 0. So the convolution of 0 gives 0. If I have a constant times the function, it pulls out, right? You can see that on either slot, because if there's a constant here, it puts a constant here, then by properties of ordinary integration, pull the constant out. That's also true. We have this distributive property, right? Because if you have f1 plus f2, that ends up putting like f1 of t minus u plus f2 of t minus u, and then you split it up to two integrals, get sum of the convolutions. It's commutative. That's a little less obvious. Here's the proof of that. G times f, g convoluted with f, I should say. Integral from 0 to t, g of t minus u, f of u du. Make a substitution. T minus u equal to w. That puts u equal to t minus w. So that makes this a w, and that flips this other thing to t minus w. And then if you write them in the opposite order, that's f star g. Okay, so it's a commutative product as well. The convolution of f of g is the same as the convolution of g and f, which is good, because it would be really weird if they weren't equal because of the defining property that they're supposed to map a product in the t domain to a product of the Laplace transforms. Well, we know the product of Laplace transforms is just a multiplication of functions of s, and that's a commutative multiplication. So if it was somehow non-commutative in the domain but commutative in its image, I know of no such thing. I mean, I don't think anyway. It's also associative. I'm not going to do that one. All right, so what good is it? Let's look at the problem. Actually, let's take a step back here. So let me take a step way back here. No, I don't want to talk about, I'm not talking about Green's functions. Well, I guess I will, but I don't want to talk about them too much in here. Yeah. Okay, so let's just recap what we're doing. We have an nth order constant coefficient differential equation, right? Equal to f of t. What do? Take the Laplace transform of that, right? We get the same polynomial but with s's instead of, we get the characteristic equation polynomial rather in s, right? And then we get the Laplace transform of our force over here. Could be discontinuous stuff, could be Dirac Delta functions. We can treat lots and lots of stuff, right? It's great. Then what's the next step? Well, the next step then is we divide by this, right? And that gives us y of s is equal to 1 over p of s times f of s, right? So now that, and then our solution then is the inverse Laplace transform of this 1 over this polynomial times the Laplace transform of the force function, right? Okay, well, you guys in engineering like to call this 1 over p of s the so-called transfer function, all right? And the reason for that is it's connected to convolution, all right? So what happens then, by the way, so let me just write down. So we have this defining, basically it's it's what makes the convolution the convolution. The convolution of f and g is equal to the product of the Laplace transform of f times the Laplace transform of g, right? Or if you like, you could say the Laplace transform of the convolution of f and g is equal to big F times big G, right? So conversely, the inverse Laplace transform of the product of two functions of s, f and g, well, that will be equal to the inverse Laplace transform of the convolution of the Laplace transform, the Laplace transform of the convolution. But of course, by definition of inverse Laplace transform, that's just what? The convolution again, right? So there you go. The inverse Laplace transform of a product of two functions is the convolution of those functions. That's fantastic. This is why convolution is interesting. So when you look at the inverse Laplace transform of 1 over the the P of S times the F of S, what do you get? That's the solution to the problem we're looking at, right? That's what we're after, the solution to the differential equation. It's given to you by the convolution, right? So he calls this thing H of S, right? So it's given by the convolution of H and little f. So the inverse Laplace transform of the transfer function is equal to the little h. This is a general method for solving the differential equation. Once you find the transfer function, you just convolute it with your force, and that's the solution. That's cool. There's so much more than this, though. What we're talking about right now, I'll go back here. I'm just talking about the nth order constant coefficient. Well, yeah, nth order constant coefficient, because my Laplace transform of the differential operator give me just the, like s to the n plus some constant times s to the n minus 1, da da da. That's assuming that we're looking at a constant coefficient nth order ODE. So any constant coefficient problem would do that. But I think it probably would still be, there's something that could be done for more general problems. There should still be some sort of transfer function for more complicated problems with variable coefficients. It's not going to be as easy to find, I would think. But I'm speculating now. I haven't worked that out. But again, just to recap, the solution, right, is the inverse Laplace transform of 1 over the characteristic polynomial of s times the Laplace transform of the force function, which is the convolution of the inverse Laplace transform of the transfer function and f. So let me just show you a specific calculation here. So here's, that's why convolution is interesting, all right? Again, how engineers think of these things. In the frequency domain, output, transfer function, input. Okay, there you go. The actual formula. So y of t inverse, and I think I've said this 4 times now. The inverse Laplace transform of the transfer function times the Laplace transform of the force is given by the convolution of the transfer function and the inverse Laplace transform of the force. But the inverse Laplace transform of the Laplace transform of the force is just the force again, duh. And this, we just derived this, is by definition the integration from 0 to t of h of t minus u, f of u du. Like that. Now, so basically, if you want the general solution, then the general solution will be, so that's actually a particular solution, right? Do you know why that's a particular solution? If you think about it, the Laplace transform I took at the start of this derivation, I just had like s to the n times y plus the coefficient s to the n minus 1 times y. What was missing was the minus like minus y of 0, minus s times y prime of 0, and so forth. I mean, s times y of 0. All the initial condition terms were set to 0, right? So basically, the thing I was just showing you assumes that the homogeneous solution is 0. So by construction, the convolution of the transfer function with the force, that thing I was just describing, that gives you the particular solution such that the homogeneous solution is 0. Actually, I think it's more than that. It gives you the solution such that it's not quite that, actually. It gives you the solution such that you've added a copy of the homogeneous solution such that y of 0, y prime of 0, y prime prime of 0, y to the nth derivative of 0 is 0. The convolution solution forces the function and all of its derivatives up to the order you're considering to be 0 at time 0. It goes back to where we started. Oops. Right here. So like when I take the Laplace transform of that down to there, I've assumed that y of 0, y prime of 0, y to the n minus 1 of 0 is 0. Everything after that builds that assumption in. So the convolution solution, again, is... I wouldn't say that it doesn't include a copy of the homogeneous solution, because it could be that your like natural particular solution is non-zero at time 0, right? So then you'd add a copy of the homogeneous solution to make that go away. That could happen, right? So anyway, long story short here, the general solution then is just this. And so it's y1c1 plus c2y2 plus cnyn, integration from 0 to t, h of t minus u f of u du. Now, I'm not telling you really how to solve a new problem. I'm giving you a different way of understanding what we've already done. See, because you could just solve the problem like we did earlier today. You take the Laplace transform of it, you find the big Y, you take the inverse Laplace transform, you find the little y. There you go, that's your solution, right? Or you go back to earlier parts of the course, use variation parameters, right? Or you use just constant coefficients and undetermined coefficients aided by the annihilator method. You have many flavor choices, right? But they can all be sort of put under this umbrella of analysis in terms of the transfer function, is the point. There's some kind of unified understanding of input and output here. All right. Here's an actual, yeah. I did a couple of examples of the transfer function just to be a little bit more specific. For example, if you have s minus r1 times s minus r2 for r1 not equal to r2, in other words, we're looking at the case of distinct real roots, second order problem, distinct real roots. You guys know the homogeneous solution, exponentials, e to the r1t, e to the r2t, right? So in this case, the transfer function is like a sum of 1 over s minus r1, 1 over s minus r2. Do the partial fractions, and you get this. The transfer function is 1 over r1 minus r2 times 1 over s minus r1, 1 over minus 1 over s minus r2. And so then that gives me the little h of t, the inverse Laplace transform of the transfer function is this. And then the general solution then is formed from convoluting that with the force. And there you go. This is an integral solution to a problem where the homogeneous solution has distinct real roots. And this if you do this integral for any force, that gives you the solution. That's 0 at time 0, with derivative 0 at time 0. You want to fit other initial conditions, add a piece of the homogeneous C1 e to the r1t plus C2 e to the r2t, and then adjust C1 and C2 as appropriate to fit whatever initial conditions you got. And that's what you do. So, for example, and then I just, to make it specific, I look at this equation, this differential equation. We have, where did I put my laser? Oh, there it is. This one here, we get r1 equals minus 1, r2 equals minus 2, right? So using my general derivation, I just went through the inverse Laplace transform of the transfer function, e to the minus t minus e to the minus 2t. So if I convolute this thing with the force, which in this case is e to the minus t. Now, you guys know e to the minus t overlaps with one of the homogeneous solutions here, right? So before we'd had to, in the method of undetermined coefficients, we had to multiply by t, right? And that's all accounted for here by the convolution. So when I integrate, but it's kind of cool how it gets accounted for. So if I evaluate this at t minus v, it's e to the minus t minus v and e to the minus 2 times t minus v. And then I multiply that by e to the minus v because that's my f of v. And some things cancel out, right? Like e to the minus v cancels with the e to the plus v from that. And this gives me plus 2v, but minus 1 gives me just plus v. And I still got e to the minus 2t. We're integrating with respect to dv, which is nice. So that means that this just is a constant with respect to v, so that's why I get v here. This is not a constant with respect to v. Well, this is the same as e to the v times e to the minus 2t. So e to the minus 2t is like a constant here. So basically, we're like, this would be something like e to the x plus 3 integrate with respect to x. You get e to the x plus 3. That's what this is like. But anyway, the integration's here, and evaluate from 0 to t. Check it out. Multiplication by t right there. So it's yet another way to explain where the t comes from in the repeated root case. Yeah. Or where overlap happens. And I should say really where overlap happens. The repeated root case is actually my next example. Actually my next example. Here I've derived the t cosine t for the case of pure resonance in the simple harmonic oscillator when you couple spring mass system. So look, this is y prime prime plus y equals to sine t. That's the homogeneous solutions here are cosine t and sine t, right? So convolution picks up the resonance calculation and it supplies the t, just like that. But I mean, is this a good trade? As you think about how you want to work problems for the final, is this a good method? I don't think so. I don't think this is a good method for a time pressure test. It's a great method for analyzing things and digging deeper into the interplay between how is your force affecting your system. It's an important qualitative tool towards getting a deeper understanding of principles of superposition and things like this. But in terms of actually solving a time pressure test question, I don't think it's a good method. Because I think undetermined coefficients is hard to beat for this problem. Because by now you should know, if I have this problem, I write down yp equals to t times a cosine plus b sine, and I work it out. It should take about 5 minutes in that way. Or if you're not sure about the t, you work through the method of annihilators. Or if some professor says work out the method of annihilators to suggest a particular solution, you do that. Some professor might do that. He's done it on previous tests, right? All right, let me go on. This one is the repeated root case in general. So like this gives you repeated root of r 2 times. The transfer function is 1 over s minus r squared. So I can calculate the inverse Laplace transform of h, right? In fact, I can use convolution to do that. So here I'm using convolution in yet a different way. The convolution of this, 1 over s minus r with 1 over s minus r should be the convolution of e to the rt with e to the rt, which is this, which works out to t e to the rt. Now, we could have also figured this out by what? I think by the Shift Theorem. And if you look at your sheet, I seem to have frozen into place. If you look at your sheet when you have it, so on here we have the, where's that stupid thing? So like the third one down in table 7.1, if you put n equals to 2, and also then the Shift Theorem. It's a combination of like the third thing on table 7.1 and the, where's that Shift Theorem gone to? Do I not have it on here? Huh. Shame on me. Well, on the other hand, shame on you, because I told you could write more stuff on there. And so the Shift Theorem said what? The Laplace transform of e to the minus at times f of t is what? the Laplace transform of f, right, at s. It's the Laplace transform of f of t at s minus a, if I remember right.
That's the third line down, table 72.
Oh, table 7.2, yeah. So, like, I mean, you could see this. Well, this isn't quite what I want either. Let me erase that. I'm not. My mind is slightly cloudy on this, so I'm going to just erase it before I do more damage than I need to. But, I mean, that I'm 50-50 on that being right, what I wrote. But my point is, you could also derive this from the shift theorem applied to the t function. It's like t times an exponential, right? So that's the same as the Laplace transform of t. And then you take s and you replace it with s minus r, right? That's the Laplace transform of t is 1 over s squared. So the Laplace transform of t times e to the rt is 1 over s minus r squared, which of course is where we were starting. But I just wanted to show you again that you could use the convolution to figure it out. Now, but I got to give you a warning. Some of you guys, like when I show students convolution, you know, it's kind of a hammer, and then everything just starts looking like a nail, you know, and that's not a good way to be. Convolution is a sledgehammer, and it requires great effort to wield it, because it requires you to do this integration correctly, right? And there are many other tools we have that are just algebraic and don't involve integration, and those tools should be used first, because you're much less likely to make a mistake with those tools. Just saying. So, oh, come on. But anyway, there's the t e to the rt solution again. You do, well, yeah, so, yeah. This is, let me just show you where this came from. This is on my website. This way I don't have to send you an annoying announcement. But if you just go to my main website right here, concerning the connection between Green's functions and the transfer functions, it's right there. See that? This is my main web page. It's just down under the schedule. I have older lecture notes and special discussions. It's right there. I think I might also have a copy in the course page. Let me look for a second here. Oh yeah, right there. See? It's at the top of the useful material and links. There it is. Now, the larger, I skipped the first couple pages of this, which are about Green's functions, all right? And so I haven't made Green's functions. No, I'm pretty sure. Yeah, I didn't make them part of the required content in this course. I would like you to know what the transfer function is and what we did just now, but I don't expect you to use it as a solution technique. What I'm trying to say is, the reason I'm saying you should understand it is I've done nothing but apply Laplace transforms with one extra definition, which is this is the transfer function, and then using convolution. So that should have been understandable, at least part of it. But I know you're not comfortable with it until you do some homework problems. To see what matters most for the next test, of course, you should look at your homework, right? So your homework will give you better insight as to what I expect from you guys. So you guys have any questions while I'm get ready to do the next thing?
Is the test next Tuesday?
That is correct. I mean, I could move it to Thursday.
Like next Thursday?
No, like this Thursday. No, next Thursday's a bad idea. We shouldn't do that. They're all lumping up then. Let's get it out of... It will help you for your finals to have it next Tuesday as opposed to next Thursday. Right? Because if you don't want to get... The more tests we get bunched up in the final exam time, the worse it gets. And sometimes it can't be avoided, like my Calc 3, but Calc 2. But here I think we could keep it Tuesday. I mean, I could conceivably move it to this Thursday. But no, I think we shouldn't do that. I don't think that would be good. That would be a good thing. Let me just say a word or two about systems with Laplace.